张slide，就第3张你讲完了，对不对？
不对啊！哦，我根本开错了，这个没错啊。
40讲完了吗？我记得这个没讲吧？这一张吗？差不多。OK， 所以这一张这个图是很重要的。This is very important figure. Okay. So, yeah. One more thing to talk about. Okay. Before we start the lecture. Okay. 今天本来是要小考。OK. 今天理论上本来是要小考。但是我忘了那个上礼拜运动会的时候，我就忘了那个把那个练习题发给你们，是不是？啊？没有公告。不，理论上2个礼拜要考1次吧？对，但是我的意思说，我考试前1个礼拜我一定会发练习题给你。OK. I'm supposed to give you like a practice question. Okay. But I forgot to do that last week because of the field day. Okay, we were too excited for the 终极标。Okay, 讲到终极标，I owe each of you 2 points. Okay, okay. I will honor my promise. Okay, 我会那个，就是说你们可以跟下一届讲哦。就是说，如果说那个总体标再拿的话，那个也会加分这样，好不好？请他们努力这样。OK， 那回到刚刚的那个小考 ，OK， 我们现在已经考了3次了，对不对 ？We already have 3 quizzes, right? 那we are supposed to have 5 quizzes according to our syllabus. So, yeah, this week, I mean, as I said, like because I forgot to post like the practice questions last week, so I will do it today. Okay, to post the practice questions today. So we will have quiz next week. Okay, 所以下礼拜我们会有一个 quiz 4. Okay, and well. 2 weeks from next week, okay? So it's about like the middle of December, we will have the last quiz. Okay, quiz 1. Okay, and according to syllabus, okay, you could drop the lowest quiz, okay, from these 5 quizzes, okay? 就是一个5次的小考里面最低的那个可以拿掉 ，OK， 算你的分数。好不好？那讲到这边有没有问题 ？OK， 所以今天是不是来的人比较多？是因为大家有人会以为是要小考，没有了，其实来的也差不多了。那个好 ，OK。
Yeah. 好。 可以。Yes。我有上传吗？上礼拜。运动会前一个礼拜就上传了。你们不是告诉我没上传吗？助教跟我讲说我没上传啊，所以我昨天才想说，那我今天就不能考试啊。所以到底是有还是没有？不好意思，因为我的宝贝助教们跟我讲，昨天晚上跟我讲我没有上传，所以我本来想说我应该就是，譬如说我下个礼拜要考，我这个礼拜上完课我就会上传，所以我应该是，如果说我上礼拜有上传，就是我上礼拜我上完课，我预计下礼拜要上课，但是运动会嘛，那我就还是先上传了，但是有上传。那你们昨天跟我讲根本是耍宝嘛？你们这个助教这样子当不太对啦，本来变成这个一个 disruption，OK， 好吧？那我们要怎么办？我们还是考？你们觉得要考？你们有准备吗？你们有准备 ？OK， 好，那我中间有一个下课，可能要花一点时间，那个一下子准备一下那个考题哦，所以OK。So if we have this quiz today, okay, which is quiz 4, right? So the next quiz will be 2 weeks from now, which will be like which date? 下礼拜是几号？12月几号？11号。Okay. So December 11th will be our last quiz. Okay. December 11th. Yeah, and I'm sorry about that because I was cheated by the TA. Okay. When TA remind me, I didn't upload the practice question. I was a little bit shocked. Okay. 好吧 Anyway. 好，那 back to the class. Okay. Okay. So last time we talked about this. Okay. This is a very, very important figure. Okay. You have to remember this. Okay. So this is, for example, each of this is like a transformation matrix from base 1 to base 3, and this one represent like this one, the linear transformation from base 2 to base 1. Okay, from base 2 to base 1. So when you put L here, okay, whatever indicated here, okay, will be your original base, and this one will be your final basis. Okay, final basis. So this is because usually we represent this. This is we have a arrow. Okay, when we use like this T is a B1 to B3. So the original basis is in the front. So that the order is slightly different. don't be cheated. Okay, don't be cheated. So for example, okay, let's say if this linear transformation from base because it goes to here, right? So this is a linear transformation from base 2 to base base 2 to base 1. Let me see. There's something wrong. Oh, sorry. This is from base 1 to base 2. Basis 1 to basis 2. So it's the order is reversed. I'm sorry about that. So both are like, for example, this T. This is from basis 1 to basis 3. This arrow obviously is a clear indication. So the other, I mean, it's always the left side is the original basis. The right side is the basis after that. So for example, okay, obviously, if you transform from basis 3 to basis 1, you should read from the right-hand side, okay, because each of these, I mean, will be considered as a matrix, right? So when you apply a matrix to a vector, whatever near the vector will be apply first, right? So 我真的觉得这有点高哦，我感觉起来这个指的地方实在是不太对。Okay, so you apply this one to your vector first. So you change from basis 1 to basis 3, and then from basis 3 back to basis 1, right? So obviously, the vector should stay the same, right? The vector should stay the same. So that's why, okay, if you combine these two, matrices, okay, it will result in identity matrices, because for no matter what vector you apply, okay, eventually it will come back to itself, right? So the combination of these matrices must be identity matrices, okay? I mean, the same goes for the other things, okay? But the other, I mean, this one is also very important, okay? So for example, okay, the linear transformation from basis 2 to basis 1, okay? So if you read it from from here, okay? From basis, basis 1 to basis 2. Okay, linear transformation from basis 1 to basis 2. It's going to be like you do base, because this is linear transformation, but this is just a basis transformation. You change the basis from basis 1 to basis 3, and then you do a linear transformation from basis 3 to basis 4. Okay, and then you transform your basis, okay, from basis 4 to basis 2. The combination of all this will be the linear transformation from basis 1 to basis 2, because this linear transformation and this linear transformation, they are supposed to be the same, right? So changing the basis wouldn't change the nature of this linear transformation. So that's why the combination of these three matrices will be the same as this one. If we use this figure as an example, okay, for example, okay, the top one, okay, if you apply the linear transformation from basis 1 to basis 2, so this is like this arrow from this one to here. It's going to be like you change the basis from basis 1 to basis 3. So you first apply T B1 to B3, and then these two linear transformations are the same. Okay, they are actually the same. Same goes for this one and this one. It's just like the bases are different. Okay, so you change the you use linear transformation to move from basis 3 to basis 4. You go here, and then from here, okay, you use the transformation from basis 4 to basis 2. So, well, it's going to be, the combination of these steps will be exactly like you do this, directly. Okay, so there are so many combinations. So, for example, the transformation from the LB1, B2, okay, you can also go this route. Okay, you do a linear transformation from basis 1 to basis 4, and then you apply like the transformation of basis from basis 4 to basis 2. So you see there are a lot of different combinations that will result in the same effect. Okay, which actually implies that these matrices, the matrices behind this each of these transformations, when you combine them, okay, they are the same. Okay. So this vector, this chart, flow chart, is very, very important. Okay, because we are going to come back to something like this shortly, hopefully today. So then we have a theorem, okay? The UVW are vector spaces. B1, B2, B3 are bases of U, V, and W, respectively, okay? And L1, okay, is a transformation from U to V, okay? And L2 is transformation from V to W, are linear transformations that A be the matrix representation of L1 with respect to B1 and B2, and B be the matrix representation of L2 with respect to B2 and B3. Then L1 combined with this is like you apply L1 to vector first, and then L2, right? So you see L1 help you to use transformation, linear transformation. Where is that? L1. Yeah, L1 is a linear transformation from U to V, right? So L1 is the matrix. Okay, the matrix A is the matrix of L1. So this is A. Okay, and after that you apply L2. So B will represent L2. So the first one is L1. Okay, and you have B1 to B2, right? Is that right? L1 is the U is B1, V is V2, and L2 is like you have B2 to B3. Okay, and then you combine these two. What you're going to get is, well, this is A, right? This is B, right? Okay. Then, your L1, B1 to B2, and then you apply L2 to B2 to B3. Okay, it's going to be just like, you apply A first and then apply B. It'll be just like that. Okay, this is just kind of just like what we discussed here. Okay, I mean, these linear transformations, they can be combined. Okay, and the result of combination is also a linear transformation. So how do we verify it is a linear transformation? We basically show that alpha V1 plus beta V2 transformation equal to alpha transformation V1 plus beta transformation B2, right? B2. We really don't need to do that. Why? We don't even need to prove that. I mean, because we just look at here. This is this is obviously a matrix, right? Okay, we know like a matrix multiplied to a vector. This is basically a linear transformation. we talked about this a lot earlier. I mean, at the beginning of this, when we talk about linear transformation, I mean, there's an example to tell you, okay, the vector multiplied by a matrix multiplied by a vector is a linear transformation. So this is a matrix, right? I mean, this is a matrix multiplied by a matrix. Obviously, the result is also a matrix, right? So this must be a linear transformation. I mean, we could verify. Okay, you can try to do that linear transformation proof by yourself. I mean, the result will be the same. Okay, but basically, okay, this is obviously the case. Okay, L2, combined with L1, okay, is a linear transformation, and the matrix representation of this one will be BA. Okay, as I mentioned here. Okay, conceptually this makes sense. Okay, just like the flow chart, but this one will be a little bit, one level higher than the flow chart, because in this flow chart we only discuss one linear transformation, right? We only discuss one linear transformation, but this one, okay, it actually tells you you can combine multiple linear transformation into one. Okay, so in other words, okay, it kind of tells you that this flow chart can be extended, right? It could be extended, okay, but yeah, of course, like if you understand this one, I mean, it's easily the extension is easy, if you understand this one, okay. So basically, okay, that'll be it. And the last one, okay, the dilation and the contraction, okay. So this Lx equal to Cx, okay. This obviously is a linear transformation, right? I mean, this x is a vector, okay, vector. So you multiply a constant to a vector. Okay, you can imagine this help you to enlarge or shrink that vector, right? Okay, and this is, this obviously is a linear transformation because C alpha x1 plus beta x2 equal to alpha cx1 plus beta cx2, right? Right? This is obviously a linear transformation, and for this we have special terminology. Okay, basically like when C the absolute value of C is less than 1. Okay, if C the absolute value of C is less than 1， 当 C 的绝对值小于1的时候 ，okay, you can imagine it shrink the original vector, right? It shrinks the original vector, so we call that contraction. Contraction 就你们英文有学过吗？还是说这变成英文课？If you don't know this word, okay, contraction is just like a shrink. Okay. Now, and then, okay, when C is greater than 1, okay, because you enlarge the vector, okay, if the absolute value of C is greater than 1, we call it this transformation as a dilation. Okay, transformation and dilation they are used more commonly in our daily words. For example, 女生生小孩，女生那个就是子宫收缩，那个收缩就是用 contraction， 那也是收缩嘛，对不对？那你如果说譬如说有人死掉了，瞳孔放大，对不对？那个瞳孔放大，那个放大用的那个词就是 dilation 哦，所以我们这个课突然变成英文课一样，反正就是 okay, you get the idea, okay? So and the reflection, okay, reflection about an axis. This is like also an easy case. 我们怎么没有？ So obviously, okay, here, okay, we confine our discussion in like a two-dimensional. Okay, it could be extended to higher dimension, but the idea is basically similar. Okay, so let's consider two-dimension. Okay, so this is your vector. Okay, so when we say refraction, okay, it is reflected based, with respect to axis. Okay, so there are two choices, obviously, right? I mean, you can do reflection over x-axis. You can do refraction over the y-axis. So assume this is xy. This vector is xy. You can imagine. Obviously, you can tell the refraction. With respect to x-axis, it will become x negative y, right? Right? It's very clear, right? Okay. So if for this type of operation, it is also a linear transformation. You can give it a try. Okay. For example, like alpha v1 plus beta v2. Try to do this. I mean, obviously, it follow like the linear transformation idea. Okay. And the other side is obviously the case. Okay, the other side is sorry, my drawing is not very good. Okay, this one will be negative x y, right? Okay, so you have two types of refraction depending on which axis you are talking about, and this could be extended into higher dimension. Right? You can do 3-dimensional, 4-dimensional refraction about an axis. And the number of possible refraction obviously depends on the number of dimensions. Okay? But you get the idea. Okay? And all this would be a linear transformation. Okay? And for the rotation is we actually already talked about rotation. I think like where is it? There's like a cosine sine something like I forgot which page you were talking about. Oh, here. This one. This is actually rotation. Okay, this is the rotation. Okay, for example, if you apply this matrix over xy, if this is the original xy, and you want to rotate this matrix, so this vector, for a theta. If this is a theta, then you just multiply this vector, okay, with this matrix. Okay, so this, we already proved that this is a linear transformation. Okay, and yeah, so well, just want you to understand this is like this represents the rotation. Okay, rotation. Well, the size stays the same. I'm sorry, my drawing is terrible. Okay, I'm not very good. I don't have very good sense in drawing. Okay. Luckily, I don't make money, in art field. Okay. So we done dilation, contraction, we done reflection, we done rotation. We haven't done translation. What is translation? Translation means like you can translate. Okay. It's not like 翻译哦，这个字有很多的意思哦。translation 当然，你学第一个翻译当然是翻译嘛，但是在数学上这不叫翻译哦。Translation means like a displacement. Okay, for example, say again like this is a vector. Okay, if you want to move this vector, okay, to a different place, for example, like move to, let's say this point is x a b. Okay, this is a b. You want to move this vector to here. So you just move to this vector to there. Okay, so obviously you can do x plus a. Okay, where a is a fixed vector. Okay, this is ab. This ab is the a represented there. Okay, it's a fixed vector. Okay, so this is not a linear transformation. You can give it a shot. Okay, because well, for example, alpha x1 plus beta x2. Okay, you apply this L. It's going to be alpha x1 plus beta x2 plus your A, right? According to definition, right? But if you try alpha L x1 plus beta L x2, it's going to be alpha x1, because this one gives you x1 plus A, right? And you multiply by alpha, so it will be plus alpha A plus, same thing, beta x2 plus beta B, beta A. So obviously these two, and this one, they are different, right? Okay, so this is not linear transformation unless A is 0. If A is 0, this term and this term disappear. So I mean, so they are obviously the same. Okay, but it's most likely not the case. Okay, 所以这个叫做就是就像说你有一个东西很大件，你不要改变它的形状，你把它移动一段一个，就是其实这个字哦，这个 translation 哦，这个在向量用的比较少。Okay, this term okay is used sparsely in vector space discussion. It is more commonly used in physics or like in mechanical engineering. Okay, 因为那个是物理或者说那种什么那个机械工程，他们会有一块东西要移动，对不对？他们有一大块东西要移动，所以他们譬如说这个东西要移动，你要把它维持这个样子，就是移动这样子，就是不要改变它的形状，移动一段就是一个距离。那个移动的这个就叫英文就叫 translation 哦 translation。OK， 那为什么我说它在 vector space discussion 比较少这样讲？因为注意到我刚刚讲那个形状，对不对？对，就是通常我们是维持它的形状，重点是维持那个形状，不需要你们不能说我改一个那个 rotate 一下不行，就是维持它的那个方向性移动过去。那在 vector 里面其实它就是一根嘛，它就是一个 direction， 所以它没有形状哦。通常我们 vector 不讲它的形状，所以 translation， yeah, you can still discuss translation in a vector space, but not as commonly used as in like mechanical engineering or physics. Okay, but so this is not so you can see like all these like physical like applications. Okay, except translation, they are all linear transformation. Okay, but what do we do about that? Okay, we could, okay, represent this one by a vector. You could represent this one with so say like if A is let's consider A as a how should I say, like if you want to talk about like X, let's imagine you consider X as a number, then you try to represent this one with like for example 1, and you have A, okay, you multiply by x1. You can represent like your translation in a form of matrix, and here, okay, so once you multiply this one, obviously it becomes x plus A, right? Okay, this can be extended to, 2-dimensional, 3-dimensional. So it's just like you discuss this translation in a different dimension. Okay, if you do that, okay, then you can sort of like transform this translation concept into a linear transformation, and then you can apply all the results we obtained in the linear transformation in the translation operation. OK， 就是说你所有的线性那个 linear transformation 的结果你都可以用过来。就是如果说你把它想成这样子的话 ，OK。Okay, so that's about it for this section. Okay, the last one is the similarity. Okay, the similarity. Yeah, this is the last section of this chapter, if I remember correctly. So what is similarity? Okay, we say A and B are n by n matrices. We say B is similar to A if there exists a non-singular matrix S such that B equal to S inverse times A times S. Okay, it looks complicated. It looks complicated. At least at first, it looks complicated. And here is an example I can give you. A is this one, B is this one. And if you have a U to be this one, and the inverse of U obviously can be calculated easily because this is 2 by 2. You know how to calculate 2 by 2 inverse easily, right? So you have this U and inverse U, and you can verify that the B equal to U inverse times A times U. Okay, this is a small example because it's 2 by 2, so it's roughly it should be easily verified. Okay, so I will not go into the detail like to calculate this. I mean, you can do this calculation by yourself. But yeah, my so why do we need to discuss similarity? Okay, it's because V is an n-dimensional vector space. L, if it's like from this vector space, if L is a linear transformation from this vector space back to this vector space, so it's n by n obviously. Okay, it's a linear transformation. So once you do, you can imagine this L. If you represent this L by a matrix, this matrix must be, the size of this matrix must be n by n, right? Okay, because it's n-dimensional, right? The V is n-dimensional. Okay, so B1 and B2 are bases of V. And the S is a transition matrix from B1 to B2. Okay, let A be the matrix representation of L with respect to B2, okay? And the B be the matrix representation of L with respect to B1. Then we have B equal to S inverse AS. So what am I talking about here? This thing is actually so easy, okay? It's so easy. Let me write it more clearly here. We finish this slide and we'll take a break. So, what is A? A is a matrix representation of L with respect. So it's like a L B. So here, okay, if you consider this as like remember that diagram, that flow chart. Let me go back to the flow chart. Okay, so this is V with respect to B1, right? And we have like a LV with respect to, let's say we say it's B1 as well. Okay, with respect to B1 as well. So, and then we have V B2. And this is the same L. Okay, L V with respect to B2. Okay, I mean, there, I mean, yeah, so, yeah, I'm allow my tardiness for like notation. You get the idea. Okay, so go back to the theorem. Okay, so what is, sorry, not this one. What is A? A is a matrix representation of L with respect to B2. So this is A. This is A. Okay, with respect to B2, right? And A is B is the matrix representation of L with respect to B1. So this is B. And what is linear the transition matrix, okay, from B1 to B2. So this is transition matrix from B1 to B2, right? Right? This is S, right? S. And we know, like, transition matrix from B1 to B2. And then we apply transition matrix from B2 to B1. It's going to be identity, right? Right? This is what we know, right? This is what we know. So, which implies that the transition matrix from B2 to B1, if this is S, this one must be S inverse, right? Right? So according to our flow chart, okay, this one, okay, what do we want? B, right? B, okay, this one must be, you apply this one first, you go this direction, right? You apply S first. Then you apply A. Okay, that move you from here to here. And then you apply S inverse. So the flow chart will tell you exactly this theorem, right? So this is what we already know. Okay, it's just like we try to write it in different manner. Okay, 我们前面已经知道，因为我们从 flow chart 其实知道这个东西，只不过现在我们是用 similarity 的 concept 来讲这个事情，但是 it represents the same thing. Okay, it is the same thing. Of course, this is a special case, to be honest, because in here, okay, this transformation is from V to W, right? From V to W. Okay, so the dimension of V and W could be different. Dimension of V and W could be different. So in that case, obviously, like your this linear transformation, the matrix represented by this linear transformation is not going to be n by n. It's not going to be square. Okay, because V and W could have different dimensions. But here, okay, in this theorem that we discussed is from V to V, right? And then the V dimension is of V is n. So that's why, okay, the underlying matrix, okay, for this linear transformation is basically n by n. Okay, this is n by n. This is n by n. This one must be n by n. Okay, why? Because it's n-dimensional. You change from one basis to another basis. So the number of bases, the number of vector in every basis of dimension n must be n. Okay, so that's so it's n by n. This is n by n. Okay. So that's it. So let's take a break and yeah, I may need shoot. Yeah, I need to use my computer to design the quiz. Okay, give me a little bit more time, and then I'll be right back.